Hey, welcome to this session about isolation in Postgres, where actually I will talk about isolation in a more broad way because what I will say will apply to most RDBMS, but we'll see that later. First, you might want to know who I am. My name is Laetitia Avro. You can find more information about me on my blog, mydbnnotebook.org. Actually, if you're familiar with my slides, you know that my slides are quite clean without text because I'm a mom and I know that when you read some text, you can't focus on what I'm saying. And as a mom, I like to be heard when I speak. So if for whatever reason you need to have more text in the slide, you will find the annotated version on my blog, mydbnnotebook.org. Just go to the Conf Talk tab and then you will find a direct link to the slide of this presentation. It's the same version, but with more words. About who I am, I'm committed to Postgres community and I'm now a treasurer for PostgreSQL Europe Association. I'm also a Postgres Women co-founder. I work for Enterprise DB as a senior database consultant, and you can follow me on Twitter under L_Avro. About the subject we are going to talk about today. So the subject is quite simple. We know about the ACID concept, but what about the I? What does the I mean? And the I, which means isolation, is more complicated than you can see. I had the idea about the conf talk when I was by a customer and I saw that because they didn't know how isolation worked and how they could adjust isolation level, they had put an extra layer in their architecture. And I hate when there are extra layers because it means that it can fail because each new component you add into your architecture can fail and you certainly don't want that. So let's begin with the beginning of everything, ACID. So ACID was funded by Jim Gray during the 70s, so it's not new concept. A is for atomicity, C is for consistency, I is for isolation, and D is for durability. Jim Gray was an engineer at IBM, and he funded a lot of things for the database world. Actually, he got a Turing Award for his work in 1998. But when he founded the concept of database, he didn't think that isolation was mandatory during the 70s. Isolation was added in 1983 with further work from two other engineers. So we will look further what this concept means. So atomicity, it's just a reminder because I'm sure you already see them either at school or during your own curiosity challenge and searches on the internet. But just to be sure we are all talking on the same thing, I will review these concepts. So atomicity just means that a transaction, if it occurs, it will be committed or rollback. But everything that happened during the transaction will be committed or rollback. You can't have half of a transaction that's being committed. It's what Wikipedia says as an atomic transaction is an indivisible and irreducible series of database operations such that either all occur or nothing occurs. Then we have the consistency. Consistency is when you design your database, you should think of how you want to be sure your data are good. Because if you have bad data in your database, you won't be able to do anything with it. So we will design and create a lot of rules that should apply to your data and that should make you more confident that your data are worth it. Wikipedia explains it in this way. Consistency in database systems refers to the requirements that any given database transaction must change affected data only in allowed ways. And the allowed ways are all the constraints you can put in a database system to be sure your data are meaningful. For example, you could decide that if you want to store the number of items you have, having a negative number has no meaning. So you could enforce a rule that says, which it's called a constraint that says that you can't have a negative data in that column because it would have no meaning at all. That's an example of constraint. About isolation now. So isolation is in a database system, isolation determines how transaction integrity is visible to other users and systems. Because if we created database, it's because we want many people to access data at the same time. Maybe to write it, maybe to read it, maybe to read it and write it. We don't know beforehand. But we need to be sure that there won't be any problem with all this person accessing the same data. That's what isolation is meant for. And that's why several levels of isolation were created. And then you have the durability. Durability is very important. It just means that once you have the commit acknowledgement, there is no way your data can be lost by the system. If it is, the system failed you and it's not good. So Wikipedia explained it in other terms. It says in database systems, durability is the asset property which guarantees that transactions that have committed will survive permanently. The important word here is committed because, of course, you can always roll back a transaction, so the rights that have been done by this transaction are not durable. Your transaction needs to be committed so that your change can be durable. So now that we are clear about these concepts from the 70s, let's go and dig into the isolation levels. So there are several isolation levels, and we see that Postgres decided that some were too light to be implemented for Postgres. We'll see that later. So first, the first level of isolation is read uncommitted. Wikipedia explains it in the way that one transaction may see not yet committed changes made by other transactions. In other words, just imagine you have two transactions going on. The first one changed the data 1, and the second one wants to read that data. It will read that data even though the first transaction had not committed these changes yet. It means that the changes might be back afterwards, but it's still been read by transaction 2. And Postgres decided that the read uncommitted mode that is available in Postgres will behave exactly like the next level, which is read committed. Does it mean that Postgres is not SQL compliant? No, of course not. It doesn't. because the SQL standard is pretty straight on that. It says that if the transaction isolation level of the SQL transaction is read uncommitted, then any level of isolation is permissible. So Postgres, by implementing read uncommitted like read committed, is still SQL standard compliant. We are relieved. Then we have the next level, which is read committed, which is the one that Postgres chooses for read uncommitted. It's an isolation level that guarantees that any data read is committed. You won't be able to read what we call dirty reads, which are data not yet committed. At the moment it is read. It means that if you have transaction 1 that is changing data, then commit these changes. Transaction 2 can see these changes, even though transaction 2 begin before the transaction 1. But as transaction 1 is completed and committed, it makes sense to read this data. It simply restricts the reader from seeing any intermediate uncommitted dirty read. Dirty read is the name of those changed data not yet committed. Then we have the repeatable read level. In this level of isolation, you can only see data committed before the transaction began. So let's assume you have transaction 1 changing one data, transaction 2 beginning before transaction 1 and trying to read the same data than transaction 1 after it's completed. It should see the value of before the change made by transaction 1. We'll see that in detail after. And the last level of isolation is serializable. It means that the repeatable read isolation, there's a glitch in my slide because it's not the right value. But serializable means that the result of the transaction will be as if the transaction were occurred one after the other. Now, why do we care about all this level of isolation? Because we quickly found out that there could be some isolation anomalies. The first isolation anomaly we found is what we call dirty read. So I already speak about that. It's a transaction when a transaction with data written by a concurrent uncommitted transaction. Here again, I emphasize on the uncommitted. Let's see how it works with an example. So if we assume you have a bank account with 100 euro on it, and then a transaction occurs which will try to retrieve 150 euros from your bank account. Let's assume also there is a constraint that says that your bank account can't be less than 0 euro. The transaction still happens because the constraints are checked only on the commit operations. So for now, the bank account balance is minus 50 euros. Then let's assume another transaction happened because you saw this wonderful pair of shoes you want to buy. So you try to buy them for 50 euros. And then your bank account balance, if you retrieve 50 euros for the minus 50 you already have not, it's now minus 100 euros. So when you try to commit the transaction for your wonderful pair of shoes, it will roll back. because of the constraint saying that you can't have a bank account less than 0. So you come back to a minus 50 bank account balance. And after that, when the first transactions that did all the mess tries to complete, of course, it will be rolled back. But let's assume that this transaction didn't happen in the same way, in the same order. What if transaction 2 had happened before? You could have been able to buy this pair of shoes because you had 100 euros in your bank account. So you should be able to pay 50 euros. But because you had this other transaction entwined with it, you weren't able to buy these shoes. Maybe it's not fair to prevent you from buying these wonderful shoes. That's dirty red. Then there is another anomaly. It's called lost update. It's a data integrity problem in which one writer of data overrides the changes of a different writer, modifying the same data. Let's see that in an example. So you have a bank account with 100 euro on it. It's the same thing. Then let's assume you have a transaction that will try to retrieve 50 euros from your bank account. So now your bank account is 50 euros. But now let's assume that there is another transaction that will try to retrieve another 50 euros from the bank account. And it does balance equal balance minus 50. So it will take the previous value and retrieve 50 euros. So it means that now you have minus, you have 0 euro on your bank account. I'm sorry, that's a glitch on my slide again. I know where the error is, but whatever. And when you try to commit, you will commit with the 50 euros minus 50 euros value. Whereas when you try to commit the other value, it will come back to the 50 euros. I'm really sorry, my slide have a lot of glitches, and this example will be corrected in the version you will see published. But the thing is, the transaction 2 committed before transaction 1, whereas transaction 1 made the change before transaction 2. And so the transaction 2 is completely erased as if nothing happened. And that could be very bad, especially for banking transactions. Now let's talk about non-repeatable read. It happens when a transaction rereads data it has previously read and finds that data has been modified by another transaction that committed since the initial read. So it's not the same thing as dirty read. It's there's a read from the data, then there's another transaction that commit a change of this data, and then the first transaction tries to reread the first data, and it will find it has completely changed. In an example, it looks that way. Let's assume that you're browsing the web and trying to buy a book. So you ask for the stock, and it says that for now there is one book, the book you want, in stock. So you say, great, I can put that in my basket. But just before, another transaction came because another customer is interested in your book, and he finds out that there's also a stock of one because it hasn't changed. So then the second customer says, okay, I would put that item in my basket. And so after that, the second transaction says, the guy decided just to complete the buy, and he complete his purchase, and so the stock is updated to 0. And when I come back and I want to buy that book, it will say to me that there's no stock. Was it said before there was stock? And so it can be a problem to say that now my transaction is rolled back because that book doesn't exist anymore. It can or cannot be a problem. It depends on your application. Sometimes you can allow such behavior, sometimes you can't. And maybe in some application, you can allow such a behavior for some transactions, and there are other transactions when you can't allow such a behavior. It really depends on your application and more of that of the transactions. Sometimes the law prevents you from doing this. Sometimes it's simply that you know that the customer will be so hungry that you don't want to do that. Then we have the phantom read. A phantom read is when a transaction re-executes a query returning a set of rows that satisfy a search condition and finds that the set of rows satisfying the condition has changed due to another recently committed transaction. So if we go and find an example about that, let's say you're browsing for a book with a title containing Slonic in it. The website says, okay, 11 books found. Here are the 1 to 10 first results, because it's something the websites love to do. It's pagination. So let's assume there's a pagination. And then a guy came up and said that there's a problem with a book because it's a duplicate. And so it removes the duplicate book from the list. And that book is The Life of Slonic. And it happens that it was the 11th book of your list. So when you come back, you want to go to next page and ask for next page, the computer system will tell you there's no such thing as a next page. That's really difficult to understand for humans. Let's put it that way. And the last anomaly is, it was actually pretty recently found because it was found during the year 2000 something for a concept that was born during the 70s. It's pretty important. So it's when the result of successfully committing a group of transactions is inconsistent with all possible orderings of running those transactions one at a time. So let's see what happens. Just assume you have 3 transactions. The first one is the transactions that will create a new ticket. So you will have the begin, then you will read the day number, and after that you will add a ticket to the day you read before, and you will commit. The second transaction is the new day transaction. It will begin, add 1 to the number of the day, and commit, and that's all. And if you look at the third transaction, it will calculate a daily imbalance for the day it read. So it begins, it reads the day number, and then it will write the imbalance of the day that was read just before, and it will commit. So now, how can that be a problem? It's when you put everything together. So let's assume the first transaction begins and read a day number. Then you will see the second transaction, new day, that begin and will add 1 to the number of the day, meaning that we are between midnight, something like that. And after that, the daily imbalance transaction begins, meaning that when you will read the day number, it will be the number that was incremented by number 2. After that, the transaction 1 keeps going and add a ticket to the day that was read before, so meaning yesterday. And after that, we write the imbalance of the day we read before, and we will commit everything. So we will have a wrong imbalance because it was calculating on the wrong day. We will have a ticket on the wrong number because the number of the day changed during the transaction. That's not satisfying. But why am I talking about isolation anomaly? Because anomalies can happen only on certain isolation levels. So for data read, it can only happen on the level of isolation read and committed. Lost update can happen on read uncommitted and read committed. Non-repeatable read can happen on read uncommitted and read committed. Phantom reads can happen on read uncommitted, read committed, and repeatable read level. And the serialization anomaly can happen on all levels except serializable as phantom read. If you look at how Postgres is implemented, it changes a little for Postgres, but the only thing is it's a little better than what the SQL standard allows. So it's not a big deal. So you see here for Postgres, you can't have a dirty read, and the phantom read can't happen during a repeatable read. That's all. So the thing is, if you want to avoid any problem, you could say that I will always be in serializable isolation model and isolation level, and I won't have any problem at all. But it's not that simple. So let's take a step back and look at some other concept. I won't have the time to explain everything to you, but I hope that you will have enough to understand what I mean. MVCC, multi-version concurrency control, is a concurrency control method commonly used by database management system to provide concurrent access to the database. It's what we use to allow people to access to the same data at the same time. And on top of that, we use what we call locks. Record locking is a technique of preventing simultaneous access to data in a database to prevent inconsistent results. It means that sometimes you will have to wait for data to be unlocked before reading or writing into it. Then there's another thing you need to know. It's deadlock. A deadlock is a state in which each member of a group is waiting for another member, including itself, to take action such as sending a message or more commonly releasing a log. It means that if you create a graph of who is locking who, you will find a cycle, and that's problematic. Let's see how it works in an example. So let's assume we have two data, two pink squares. So the first transaction said that the data one should be blue. So it changes the data, and by doing it, it will lock that data. The second transaction comes and says that data 2 should be green. So by doing so, it will lock again data 2. And then data 1 comes back and say, okay, transaction 2 come back and says, now data 1 should be green. And transaction 1 come back and say, now data 2 should be blue. And there's no way you can get out of this situation because each one is waiting on the other transaction. The other way to resolve this is to kill one of the transactions, and that's exactly what Postgres does. So why am I talking about logs, about FSCC on an isolation conf talk? It's because if you take a step further in the isolation level you choose, you will have more logs, meaning you will have more time waiting, and you will have a more high probability to have a deadlock. So it's a trade-off. So if you're a developer and you want to use that knowledge, what should you do? So the only thing you can do is you have to question yourself. Is it okay to have dirty reads? Is it okay to have lost updates? Is it okay to have non-repeatable reads? Is it okay to have phantom reads? Is it okay to have serialization anomaly? And when you answer to each of these questions, you will know which kind of isolation level you need in this particular transaction. So, in most of the time, it's probably not okay to have dirty reads. Well, most of our DBMS system now will by default not allow dirty reads. There are some systems that allow it, but most of the time it doesn't. Is it okay to have lost updates? Well, most of the time, probably it's okay. Because anyhow, if someone wants to change a data after it's been modified by another transaction without any concurrency in those two transactions, you will let the second transaction modify the data. So most of the time, you will be okay with lost updates. Is it okay to have non-repeatable read? Well, most of the time, you'll probably be okay. Is it okay to have phantom reads? Again, you'll probably be okay with that. And serialization anomalies? Yes, you definitely should be okay with that most of the time. It's really, it's the use case when you can't have a serialization anomaly. It's really, really tiny. So most of the time, you will go with a red committed isolation level. And it's a good thing because it's a good trade-off between logs and waiting and isolation level and how you will have concurrency access. It's the default level for Postgres, but it's also the default level for most RDBMS. Then pagination. Is it okay to have dirty reads? Probably not. Is it okay to have lost updates? Probably not. Is it okay to have non-repeatable reads? Well, it depends. Sometimes you'll be okay with having a pagination where your 11th item of your list disappear when you click next. Sometimes you won't be okay. It really depends on your context. Is it okay to have phantom reads? Probably. Is it okay to have serialization anomaly? Probably. So in this case, you should go with rate committed or repeatable read. It really depends on your context. How about inventory levels? So for an inventory level, is it okay to have dirty reads? Probably not. Lost updates? Probably not. Non-repeatable reads? Probably not. Phantom reads? Maybe not. And serialization anomaly? Yes, you should probably be okay with serialization anomaly. So in that particular case, you would like to have repeatable read. Then the last one is invoice number. I don't know in other regulation, but in France, for an invoice number, you can't have holes in your sequence. That's one thing. And the second thing is you really need to be straightforward with the numbers. So in that particular case, as you can't use a sequence because you can't have holes, and you need to be sure that there's no two transactions incrementing the number at the same time, because you might have troubles with the numbers and end up. So what you need in that case is you can't afford serialization anomalies. That's why in that particular case, I really encourage you to look at the serializable isolation number. So to conclude, I think that every developer could look at isolation level, play with it, try several transactions, and try to see how it looks, how it works, and how it could be a good thing for the application to change that. And I really think that there should be more messages between DBAs and developers to make things better. And I hope that this talk will help in that way. And I'm open to any comments or question, of course. So I think that now it's the time for question. Do you have any question? Okay, I guess I was pretty clear about what isolation is and what it means for your application. So thank you very much for attending, and I see you around in the conference somewhere.